Tonight we're going to confront one of the strangest facts about reality. The universe has a speed limit. Not a suggestion, not a barrier we haven't broken yet. A hard, absolute, non-negotiable maximum speed built into the fabric of existence itself. And here's what makes this truly bizarre. It's not about light. Light just happens to travel at this speed because it has no mass. The speed limit would exist even if light didn't. It's woven into the structure of space and time themselves. It determines what can cause what can influence what, and what regions of the universe are forever cut off from each other. Most people think of the speed of light as just a very fast speed, but it's not a speed in the way you normally think of speed. It's something far deeper, and by the end of tonight, you're going to understand why the universe couldn't function without it. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now let's begin. Let's start with something you already understand: speed. You deal with it every day without thinking about it. You walk at about 5 kilometers per hour. You drive at maybe 100. A commercial airplane flies at about 900. Speed is simple. It's just how far something moves in a certain amount of time. Distance divided by time, nothing complicated about it. And when you combine speeds, they add up in a way that feels completely obvious. If you're standing on a train moving at 80 kilometers per hour and you throw a ball forward at 20 kilometers per hour relative to the train, someone watching from the platform sees the ball moving at 100 kilometers per hour. 80 plus 20. That's just common sense. You don't need a physics degree to understand that. It's the kind of thing you learn as a child without anyone even teaching you. You feel it intuitively when you toss something while riding in a car. You experience it when you walk forward on an airplane and reach the bathroom a little faster than someone walking the same speed back in the terminal. Speeds stack, they add up, they combine. This is so basic, so deeply embedded in how we understand motion, that questioning it seems absurd. Why would speeds not add up? What possible reason could there be for the universe to work any other way? For over 200 years, nobody questioned this. Isaac Newton built his entire framework of mechanics on it. In Newton's universe, space was a fixed stage, an enormous, infinite, unchanging container that everything existed inside. Time was separate, ticking along at the same rate for everyone, everywhere. A clock on Earth, a clock on Jupiter, a clock flying through the galaxy at tremendous speed. They all ticked at exactly the same rate because time was universal, absolute. It didn't care what you were doing or how fast you were moving, it just marched forward. In this framework, adding speeds made perfect sense. Space was fixed, time was fixed, and if two velocities pointed in the same direction, you simply added the numbers together. If you were running at 10 kilometers per hour on a train moving at 50, you were going 60 relative to the ground. No exceptions, no complications, no surprises. This worked brilliantly for centuries. Newton's laws explain the motion of cannonballs, the orbits of planets, the mechanics of machines. They launched the Industrial Revolution. They predicted where comets would appear. They described how bridges bear weight and how rivers flow. Everything in the everyday world confirmed what Newton said. Speeds add up, space is fixed, time is absolute. Nobody had any reason to doubt any of this. The first hints that something deeper was going on came from a completely unexpected direction: light. By the mid-1800s, physicists had made enormous progress understanding light. James Clerk Maxwell, a Scottish physicist, published a set of equations in 1865 that unified electricity and magnetism into a single framework called electromagnetism. These equations were beautiful. They described how electric fields create magnetic fields, and how magnetic fields create electric fields. And they predicted something remarkable. They predicted that oscillating electromagnetic fields should travel through space as waves. When Maxwell calculated the speed these waves should travel at, using only known electrical and magnetic constants that had been measured in laboratories, he got a number: about 300,000 kilometers per second. This was already known to be approximately the speed of light. Maxwell realized that light itself was an electromagnetic wave. Visible light, radio waves, ultraviolet, infrared. All of them were the same phenomenon, travelling at the same speed. This was a stunning unification, but there was something strange buried in Maxwell's equations. The speed of these electromagnetic waves was fixed by the equations themselves. The equations didn't say light travels at 300,000 kilometers per second relative to whatever emitted it. They just said light travels at 300,000 kilometers per second, period. No reference point, no relative to what, just a flat, universal number baked into the mathematics. This was odd. In Newton's world, every speed was relative to something. A car going 60 kilometers per hour is going 60 relative to the road. Relative to another car going 50 in the same direction, it's going 10. Relative to a car going 60 in the opposite direction, it's going 120. Speed always depended on who was measuring it. There was no such thing as a speed without a reference frame, but Maxwell's equations seemed to be saying that light had an absolute speed. It travelled at 300,000 kilometers per second, no matter what. This didn't fit Newton's framework at all. Most physicists at the time assumed there must be a medium, some invisible substance filling all of space through which light travelled. They called it the luminiferous ether. The idea was simple. Just as sound waves travel through air and water waves travel through water, light waves must travel through something. The ether was supposed to be that something. It would be perfectly transparent, completely weightless, and fill every corner of the universe. Light speed of 300,000 kilometers per second would be its speed relative to the ether, just as the speed of sound is measured relative to the air. This would save Newton's rules. Speeds would still add up. If you moved through the ether at some speed and shone a flashlight forward, the light would move at 300,000 kilometers per second relative to the ether, but at a different speed relative to you, just like throwing a ball on a train. The ether would be the universal background, the absolute reference frame against which all motion could be measured. It was a perfectly reasonable idea given everything they knew at the time, and it was completely wrong. In 1887, two American physicists, Albert Michelson and Edward Morley, designed one of the most important experiments in the history of science. Their goal was to detect Earth's motion through the ether. The logic was straightforward. Earth orbits the Sun at about 30 kilometers per second. If the ether existed and was stationary relative to the Sun or the stars, then Earth would be ploughing through the ether like a boat through water. Light travelling in the direction of Earth's motion should be moving at a slightly different speed than light travelling perpendicular to Earth's motion. The difference would be tiny, but Michelson had invented an instrument called an interferometer that could measure extraordinarily small differences in the speed of light by comparing two beams travelling in perpendicular directions. The experiment was brilliant in its design. Michelson and Morley split a beam of light into two perpendicular paths, let each beam travel a certain distance and reflect back, then recombined them. If the beams travelled at different speeds because one was going with or against the ether wind and the other across it, the recombined beams would be slightly out of phase with each other. This phase difference would show up as an interference pattern, a specific arrangement of light and dark fringes that was extraordinarily sensitive to even the tiniest speed differences. They expected to see a shift in the interference pattern as they rotated the apparatus. After all, Earth was moving through the ether at 30 kilometers per second. That should produce a measurable difference. They ran the experiment. They rotated the apparatus. They checked and double-checked their results. And they found nothing. No shift, no difference, no sign of the ether whatsoever. Light travelled at exactly the same speed in every direction regardless of Earth's motion. This was one of the most important null results in scientific history. Michelson and Morley tried again. They improved the equipment. They ran the experiment at different times of year when Earth was moving in different directions through its orbit. Nothing changed. The speed of light was the same in every direction, always. The ether didn't seem to exist. This result baffled the physics community. How could light travel at the same speed regardless of the observer's motion? If you're moving toward a light source, shouldn't the light reach you faster? If you're moving away, shouldn't it reach you slower? That's how every other type of motion worked. Throw a ball toward a moving person, and it reaches them sooner than it would if they were standing still. This is basic kinematics. But light didn't obey these rules. Physicists tried to rescue the ether hypothesis. The Dutch physicist Hendrik Lorentz and the Irish physicist George Fitzgerald independently proposed that objects moving through the ether physically contracted in the direction of motion. This length contraction would be exactly the right amount to compensate for the expected speed difference, making the Michelson-Morley experiment show a null result, even though the ether existed. Lorentz developed a complete mathematical framework, a set of equations now called the Lorentz transformations, that described how lengths and times would change for objects moving through the ether. These equations worked. They explained the null result perfectly, but they required a strange assumption. Physical objects actually shrank when they moved. Not because anything pushed on them, not because of any force, just because motion through the ether somehow caused matter to contract. Nobody could explain why this would happen. It felt like a mathematical trick designed to save a theory that was failing. And then, in 1905, a 26-year-old patent clerk in Bern, Switzerland, changed everything. Albert Einstein published a paper called On the Electrodynamics of Moving Bodies. In it, he did something radical. Instead of trying to explain why light's speed was constant by invoking length contraction or ether winds, he simply accepted it as a fundamental fact and worked out the consequences. Einstein proposed two postulates, two starting assumptions from which everything else would follow. First, the laws of physics are the same for all observers moving at constant velocity relative to each other. There is no privileged reference frame, no absolute rest, no ether. Second, the speed of light in a vacuum is the same for all observers, regardless of their motion or the motion of the source. That's it, two statements. And from those two statements, Einstein derived the most profound revolution in our understanding of space and time since Newton. The consequences were staggering. If the speed of light is the same for everyone, then something else has to give. When you're on a train and throw a ball forward, speeds add up because space and time are fixed. Everyone agrees on distances. Everyone agrees on how much time has passed. But if light speed is constant for all observers, then distances and times cannot be the same for everyone. They have to change. Einstein showed that time itself runs at different rates for observers moving at different speeds. This is time dilation. A clock moving relative to you ticks slower than your clock. Not because the clock is broken, not because something is wrong with it. Time itself is passing more slowly for the moving clock. This isn't a metaphor. It isn't an optical illusion. It's a real, physical effect. Time genuinely passes at different rates depending on how fast you're moving. He also showed that lengths contract in the direction of motion. A ruler moving past you at high speed is genuinely shorter than an identical ruler at rest. Not because it's been squeezed, not because your eyes are tricked. The ruler is physically shorter because space itself is contracted for moving objects. These are the same equations Lorentz had derived, the same Lorentz transformations. But Lorentz had interpreted them as mechanical effects of moving through the ether. Einstein interpreted them completely differently. There was no ether. There was no mechanical contraction. Space and time themselves were different for different observers. The transformations weren't describing what the ether did to matter. They were describing the fundamental geometry of reality. This distinction is crucial. Lorentz thought the equations were about stuff moving through a medium. Einstein realized the equations were about the structure of the universe itself. Same mathematics, completely different meaning. And the meaning changes everything. Let me try to make this concrete because it sounds abstract. Imagine two people, Alice and Bob. Alice is floating in space, not moving. Bob flies past her at 80% the speed of light in a spacecraft. As Bob passes, Alice looks into his spacecraft through a window. She sees his clock running slow, genuinely slow. If she watches for what she measures as 10 seconds, she sees Bob's clock tick only 6 seconds. Bob's heartbeat is slower. His thoughts are slower. Every physical process in his spacecraft is happening more slowly from Alice's perspective. Now here's the strange part. Bob, sitting in his spacecraft, notices nothing unusual. His clock ticks at the normal rate. His heart beats normally. He feels completely fine. But when Bob looks out the window at Alice, he sees her clock running slow. He sees her heartbeat slow, her processes slow. From Bob's perspective, it's Alice whose time is dilated, not his. Both observers see the other's clock running slow. This sounds like a contradiction. How can each person see the other's time running slow? The resolution lies in the fact that they're measuring different things. They're in different reference frames, and the concept of the same moment is different for each of them. Simultaneity, the idea that two events happen at the same time, is not absolute. Two events that happen at the same time according to Alice might happen at different times according to Bob. This is the most radical part of Einstein's theory. Not just that time runs at different rates, but that the very notion of now, of this moment, of what is happening right now across the universe, depends on how you're moving. There is no universal now. There is no cosmic clock ticking away in the background that everyone agrees on. Each observer has their own time, their own now, their own sequence of events, and all of them are equally valid. None of them is more correct than any other. Einstein himself devised a thought experiment that makes this shockingly clear. Imagine a long train moving at tremendous speed along a straight track. A person is standing on the platform right at the midpoint of the train as it passes. At the exact moment the midpoint of the train passes the person on the platform, two lightning bolts strike. One hits the front of the train, one hits the back. From the perspective of the person standing on the platform, the two strikes happen at exactly the same time. The light from both strikes travels at the same speed toward the platform observer. Since the observer is equidistant from both strike points, the light from both bolts reaches the observer at the same instant. Simultaneous, no question about it. But now consider a passenger sitting exactly in the middle of the train. This passenger is also equidistant from both strike points. But the passenger is moving. The train is carrying the passenger toward the front lightning strike and away from the rear one. Light from both strikes travels at the speed of light, not at the speed of light plus the train's velocity or minus the train's velocity, just the speed of light, always the same regardless of the observer's motion. That's Einstein's postulate, confirmed by every experiment ever conducted. Because the passenger is moving toward the front of the train, the light from the front strike reaches the passenger first. The light from the rear strike, which has to chase the passenger who is moving away from it, arrives slightly later. The passenger concludes that the front bolt struck before the rear bolt. These two events were not simultaneous. They happened at different times. And here's the critical point. Neither observer is wrong. The platform observer, using perfectly valid physics and measurements, concludes the strikes were simultaneous. The train passenger, using equally valid physics and equally accurate measurements, concludes they weren't. Both are correct. Simultaneity is not a fact about the universe. It's a fact about your reference frame. It depends on how you're moving. Two events that are simultaneous for one observer are not simultaneous for another observer moving at a different velocity. This isn't a trick of perception. It isn't because one observer has better clocks or a clearer view. It's because time itself is different for observers in different states of motion. The universe doesn't have a universal clock assigning a single timestamp to each event. Events don't have a single when that everyone agrees on. The when depends on the who, on how that observer is moving through space-time. This shatters our everyday intuition more thoroughly than almost anything else in physics. We are deeply wired to believe in a universal now. We feel that right now, at this very instant, there is a definite state of the entire universe. The moon is in a specific place. A star in a distant galaxy is in a specific phase of its life. An alien on a distant planet is doing a specific thing, all right now. But Einstein showed that right now has no universal meaning. Your right now is different from the right now of someone moving at a different speed, and neither of you is more correct. The universe simply doesn't have a single present moment that everyone shares. It has as many present moments as there are observers, each one equally valid, each one slicing through the four-dimensional block of space-time at a slightly different angle. This is why speeds don't simply add up at high velocities. In Newton's world, if Bob is moving at 80% of light speed and shines a flashlight forward, Alice should see the light moving at 180% of light speed, 80 from Bob plus 100 from the light. But that doesn't happen. Alice sees the light moving at exactly 100% of light speed, the same speed she'd measure if Bob were standing still. How? Because time and space adjust. Bob's time is dilated, his distances are contracted. And when you account for these changes using the Lorentz transformations, the velocities don't simply add anymore. They combine according to a different formula, one that always keeps the result below the speed of light. No matter how fast Bob is moving, and no matter how fast something moves relative to Bob, Alice will never measure anything exceeding the speed of light. The mathematics guarantees it. The Lorentz transformations make it structurally impossible for any combination of speeds to exceed 300,000 kilometers per second. This isn't a coincidence, it's a consequence of the geometry of space-time itself. When Einstein worked through the implications, he found something that went far beyond just correcting Newton's velocity addition formula. He found that the speed of light isn't really about light at all. Light happens to travel at this speed because it has no mass. Photons, the particles of light, have zero rest mass, and anything with zero rest mass must travel at exactly this speed. Not approximately, exactly. It cannot go faster, it cannot go slower. It must travel at 300,000 kilometers per second, from the moment it's created to the moment it's absorbed. But the speed limit itself has nothing to do with the properties of photons. It has to do with the properties of space-time. Einstein's equations reveal that there is a maximum speed at which any information, any influence, any causal connection can propagate through the universe. This speed emerges from the mathematical structure of space and time. It would exist even in a universe with no light at all. If you somehow had a universe where photons didn't exist, but everything else was the same, the speed limit would still be there. Exactly the same value. Exactly the same consequences. Other massless things would travel at it. Gravitational waves, for instance, also travel at exactly this speed. Not because they're related to light, but because they're massless disturbances propagating through space-time. The speed limit is a property of the stage, not of the actors. This is why physicists sometimes prefer to call it the speed of causality, rather than the speed of light. The name speed of light is a historical accident. We discovered the speed through studying light because light was the first thing we found that travelled at this maximum speed. But calling it the speed of light gives the wrong impression. It makes it sound like this is a property of light, something special about photons, something about electromagnetic radiation. It's not. It's a property of the universe, a structural feature of space-time geometry that constrains everything, not just light. Think of it this way. The speed of sound is about 343 meters per second in air at sea level. But that's not really a property of sound. It's a property of air. Sound is just pressure waves travelling through air molecules. The speed at which those waves propagate depends on the air's temperature, density, and composition. Change the medium, and the speed changes. Sound travels faster in water, faster still in steel. The speed of sound isn't fundamental, it's a consequence of the medium. In a similar but much more profound way, the speed of light is a consequence of space-time itself. Space-time is the medium, and 300,000 kilometers per second is the rate at which causal influence propagates through it. But unlike the speed of sound, which varies from medium to medium, the speed of light is universal. It's the same everywhere. It doesn't depend on conditions. It doesn't change based on what's happening. It's a fixed, fundamental, unchangeable constant woven into the deepest structure of reality. Why? Why should there be a maximum speed at all? This is the real question. The question most people never ask because they're too busy learning what the speed of light is to wonder why it exists. In a Newtonian universe, there is no speed limit. You can go as fast as you want. Apply enough force for long enough, and you can reach any speed. There's nothing in Newton's equations that prevents this. You can accelerate forever, piling up speed without bound. 10 kilometers per second, 1 million, 1 billion, 1 trillion. No ceiling, no wall, no barrier. But our universe isn't Newtonian. Our universe has a fundamentally different structure. And that structure, as we're about to see, makes a speed limit not just possible, but necessary. The existence of this limit is not some arbitrary rule imposed from outside. It's not like a speed limit sign on a highway that some cosmic engineer posted. It emerges inevitably from the way space and time are connected. And understanding that connection is one of the most important things you can ever learn about the nature of reality. What the Michelson-Morley experiment revealed, what Einstein formalized, what a century of subsequent experiments has confirmed beyond any reasonable doubt, is that we don't live in Newton's universe, we live in Einstein's. And in Einstein's universe, space and time are not separate, fixed, absolute entities. They are woven together into a single, unified structure. They stretch, they bend, they warp, they trade off against each other in precise mathematical ways. And that interconnection, that deep entanglement between space and time, is exactly what creates the speed limit. Every experiment we've ever conducted at high speeds confirms this. Every particle accelerator, every atomic clock flown on an airplane, every GPS satellite transmitting timing data from orbit, all of it shows the same thing. The universe has a maximum speed for the transmission of information and causal influence. That speed is approximately 299,792 kilometers per second, and nothing, absolutely nothing, can exceed it. Not because we lack the technology, not because our rockets aren't powerful enough, but because the fabric of reality itself is structured in a way that makes exceeding this speed a logical impossibility. It would be like trying to go north of the North Pole. The question doesn't even make sense given the geometry you're working with. And to understand why, we need to go deeper. We need to understand what it really means for space and time to be the same thing. In 1908, 3 years after Einstein published his special relativity paper, a mathematician named Hermann Minkowski stood before an audience of scientists in Cologne, Germany, and said something that would reshape how humanity understands the universe. He declared that from that point forward, space by itself and time by itself were doomed to fade away into mere shadows. Only a kind of union of the two would preserve an independent reality. Minkowski had been one of Einstein's professors at the Swiss Federal Polytechnic in Zurich, and now, studying his former student's work, Minkowski saw something Einstein himself hadn't fully emphasized. Special relativity wasn't just saying that space and time behave strangely at high speeds. It was saying that space and time are two aspects of a single entity, not separate things that interact, one thing that can be viewed from different angles. Minkowski called this unified entity spacetime, and his insight was not merely philosophical, it was geometric. He showed that everything Einstein had derived, time dilation, length contraction, the constancy of light speed, all of it could be understood as simple geometry in a four-dimensional structure. 3 dimensions of space and 1 dimension of time fused together into a single four-dimensional fabric. This might sound abstract, but it's one of the most concrete and powerful ideas in all of physics, and it is the reason the universe has a speed limit. To understand what Minkowski meant, let's start with something simple. Ordinary space in 2 dimensions. Imagine a flat piece of paper. You can describe any point on that paper using 2 numbers, an x-coordinate and a y-coordinate. If you want to know the distance between 2 points, you use the Pythagorean theorem. The distance squared equals the difference in x squared plus the difference in y squared. Simple geometry that you probably learned in school. Now here's something important about distance on that flat paper. It doesn't depend on how you orient your coordinate system. You can rotate the paper, you can tilt your x and y axes, you can measure from a different angle, but the distance between 2 points stays the same. If 2 points are 5 centimeters apart, they're 5 centimeters apart regardless of which direction you call x and which direction you call y. The individual coordinates change when you rotate, but the distance, the actual physical separation, doesn't change. Distance is what mathematicians call an invariant. It's a quantity that remains the same no matter how you look at it. The coordinates are just your perspective. The distance is the reality. Minkowski discovered that spacetime has an analogous invariant, but it's not quite the same as ordinary distance. In regular space, you add the squares of the coordinate differences. In spacetime, you do something slightly different. You subtract. The space-time interval between two events is the time separation squared minus the space separation squared, with appropriate conversion factors involving the speed of light. This subtraction, this minus sign, changes everything. It's the single most important detail in all of relativity. That minus sign is what makes space-time fundamentally different from ordinary four-dimensional space. It's what creates the speed limit. It's what separates cause from effect. It's what makes the universe work the way it does. Let me unpack what this means. In ordinary space, if you know 2 points, you can always find a straight line path between them. The distance is always positive. You can always get from one point to another. But in space-time, because of that minus sign, the interval between two events can be positive, negative, or zero. And which one it is determines the fundamental relationship between those events. If the time separation between two events is larger than the space separation divided by the speed of light, the interval is called time-like. This means there's enough time between the events for a signal travelling at or below the speed of light to get from one to the other. A cause at the first event can produce an effect at the second. They're causally connected. Something happening at one event can influence what happens at the other. If the space separation is larger than the time separation multiplied by the speed of light, the interval is called space-like. This means the events are too far apart in space and too close together in time for any signal, even one travelling at the speed of light, to connect them. Nothing that happens at one event can possibly influence what happens at the other. They're causally disconnected. Neither can be the cause of the other. They exist in each other's absolute elsewhere, a region of space-time that is fundamentally unreachable no matter how fast you go. And if the space separation equals the time separation multiplied by the speed of light, the interval is zero. This is called a null interval or light-like interval. This is the path that light follows. Light always travels along paths where the space-time interval is exactly zero. This is not a coincidence. It's the definition of what it means to travel at the speed of light through space-time. These three categories, time-like, space-like, and light-like, create a structure at every point in space-time called a light cone. Imagine an event, something that happens at a specific location at a specific time. Now imagine all the paths light could take from that event, spreading outward in all directions. In 2 dimensions of space plus 1 of time, this traces out a cone shape. Light going forward in time creates the future light cone. Light going backward in time traces the past light cone. Everything inside the future light cone is the set of events that can be influenced by the original event. Everything inside the past light cone is the set of events that could have caused the original event. Everything outside both cones is causally disconnected, unreachable, uninfluenceable. The light cone is the boundary between what can affect you and what cannot. It's the edge of your causal reach, and it's determined entirely by the speed of light, not by technology, not by engineering, by the geometry of space-time itself. This is why the speed of light is a speed limit. The light cone structure is built into the fabric of reality. Exceeding the speed of light wouldn't just mean going very fast, it would mean crossing outside your own light cone. It would mean reaching events that are space-like separated from you. Events that, by the geometric structure of space-time, cannot be causally connected to you. And here's where it gets truly strange. If you could somehow cross outside your light cone, if you could somehow travel faster than light, you wouldn't just be going very fast. You'd be travelling into what other observers would call the past. This isn't science fiction speculation. It's a direct mathematical consequence of the Lorentz transformations. In special relativity, different observers moving at different speeds disagree about the order of space-like separated events. If 2 events are outside each other's light cones, some observers will say event A happened first and event B happened second. Other observers, moving at different velocities, will say event B happened first and event A happened second. And both are equally correct, because there's no absolute time ordering for space-like separated events. Now, if you could send a signal faster than light, you could send information between space-like separated events. And since different observers disagree about which event came first, some observers would see your signal arriving before it was sent. You would have sent a message into the past. This creates paradoxes. You could send a message telling someone to prevent the message from being sent. If they succeed, the message never existed, so they never received it, so they never prevented it, so the message does exist. This is a logical contradiction. The universe cannot contain logical contradictions. Therefore, the universe cannot allow faster-than-light signaling. The speed limit isn't a practical barrier. It's a logical necessity. The geometry of space-time, with its minus sign in the interval formula, creates a causal structure that would collapse into paradox and contradiction if the speed limit were violated. The universe has a speed limit because without one, cause and effect would be meaningless. Now let me introduce perhaps the most beautiful and intuitive way to understand why the speed limit exists. This is an idea that emerged from Minkowski's geometric framework, and once you grasp it, the speed limit stops being strange and starts feeling inevitable. Everything in the universe is always moving through space-time at the same total rate, always, without exception, and that rate is the speed of light. This sounds bizarre at first, so let me explain carefully. You have two ways to move through space-time. You can move through space, which is what we normally call motion, and you can move through time, which is what we normally call just existing, aging, experiencing the passage of time. These two types of motion are connected. They share a budget. The total rate at which you move through space-time is always fixed at the speed of light. You can allocate this budget differently, but you can never exceed it. When you're sitting perfectly still, not moving through space at all of your motion through space-time goes into moving through time. You're racing through time at the maximum possible rate. Your clock ticks as fast as it possibly can. Time flows at full speed for you. This is your default state. Maximum time, zero space. Now imagine you start moving through space. You get in a car, you start driving. Some of your space-time budget now goes into spatial motion, but the total budget is fixed. So if more of it goes into moving through space, less of it is available for moving through time. Your clock slows down. Time passes more slowly for you compared to someone who is stationary. This is time dilation, and it's not a side effect of motion. It is motion. You've redirected some of your inevitable motion through space-time away from the time direction and into the space direction. The faster you move through space, the more of your budget goes to spatial motion and the less is left for temporal motion. Your clock slows down more and more. At everyday speeds, this effect is incredibly tiny. A car moving at 100 kilometers per hour redirects such a minuscule fraction of its space-time budget from time to space that the time dilation is immeasurably small, a few extra nanoseconds over the course of a lifetime, completely undetectable without atomic clocks. But the effect is real, and at higher speeds it becomes dramatic. At 50% of the speed of light, time dilation becomes noticeable. A clock moving at half light speed ticks about 13% slower than a stationary clock. At 90% of the speed of light, the effect is extreme. A clock moving at 90% light speed ticks less than half as fast. At 99%, the moving clock ticks about 7 times slower. At 99.99%, it ticks about 70 times slower. And as you approach the speed of light, your entire space-time budget gets consumed by spatial motion. There's nothing left for temporal motion. Time stops. A photon, travelling at the speed of light, uses its entire space-time budget on moving through space. It has nothing left for moving through time. From a photon's perspective, if such a perspective even makes sense, time does not pass. A photon is emitted from a star and absorbed by your retina, and from the photon's own frame of reference, those two events happen at the same instant. The photon doesn't experience travel time. It doesn't age. It exists in a frozen moment, its entire existence compressed into a single instant of its own time, even if millions of years pass in our frame. This is why nothing with mass can reach the speed of light. To reach light speed, you would need to redirect your entire space-time budget to spatial motion, leaving zero for temporal motion. Your time would have to stop completely. But to do this, you would need to be accelerated by an infinite amount of energy, and the universe doesn't contain infinite energy, so you can approach light speed, getting closer and closer, your clock ticking slower and slower, but you can never quite reach it. There's always a tiny sliver of your budget still going into time. You can make it as small as you want, but you can never make it zero. This is why the speed of light is a limit, not because something stops you, not because there's a wall or a barrier, but because of how space-time allocates motion. You have a fixed budget. You can spend it on space or time, but you can't exceed it. Moving at the speed of light means spending all of it on space, which requires infinite energy for anything with mass. The budget is the constraint, the geometry is the limit. Think of it like a compass needle. A compass needle always points somewhere. It has a fixed length. You can rotate it so it points more north and less east, or more east and less north, but the total length of the needle never changes. If it's pointing entirely north, it has 0 east component. If it's pointing entirely east, it has 0 north component. It can point in any direction, but the magnitude stays constant. Your motion through space-time is like that needle. Its total magnitude is always the speed of light. You can rotate it so more of it points through space and less through time, but the total never changes. Light speed isn't a speed you can reach or exceed. It's the total magnitude of your motion through space-time. It's always there. You're always moving at light speed through space-time. The question is just how that motion is distributed between space and time. The most vivid way to see what this budget really means for human experience is through the twin paradox. Imagine two identical twins, Anna and her sister Beth. Anna stays on Earth. Beth boards a spacecraft capable of travelling at 95% of the speed of light. Beth rockets away from Earth, travels to a star about 10 light-years distant, turns around and comes back. From Anna's perspective on Earth, the journey is straightforward to calculate. Beth is travelling at 95% of light speed to a star 10 light-years away. The outbound trip takes a little over 10.5 years. The return trip takes the same. When Beth's spacecraft finally lands, Anna has aged about 21 years. She's older. Her hair might be greying. She's lived through 2 decades of life, relationships, seasons, experiences. But when Beth steps off the spacecraft, she has aged only about 6.5 years. She looks barely different from the day she left. Her biological clock, her heartbeat, her cellular aging, every physical process in her body has been running slower for the entire journey. Not because something was wrong with her, not because space travel preserved her youth through some mysterious mechanism, but because she was moving through space at 95% of the speed of light, which means her space-time budget was almost entirely allocated to spatial motion. Very little was left for temporal motion. Her clock ticked slower. Her time passed slower. She aged less. This is real. This would actually happen. It's not a thought experiment that breaks down when you examine it carefully. It's a direct, unavoidable consequence of the space-time budget. Anna, sitting on Earth, moved almost entirely through time for 21 years. Beth, hurtling through space, diverted most of her space-time motion into the spatial direction, leaving far less for the temporal direction. When they reunite, the difference is permanent. Beth is genuinely, physically, biologically younger than her twin sister. She didn't just experience less time actually passed for her. Her atoms aged less. Her cells divided fewer times. Her heart beat fewer beats. The effect is not symmetric. This is the paradox part, and it confuses many people. Earlier we said Alice sees Bob's clock running slow, and Bob sees Alice's clock running slow. So why isn't the twin situation symmetric? Why doesn't Beth see Anna as the younger one when they reunite? The answer is that the twin situations are not equivalent. Anna stays in a single reference frame the entire time. She never accelerates. She drifts through space-time on a straight path. But Beth accelerates. She changes direction. She has to slow down, stop, turn around, and accelerate back toward Earth. That turnaround breaks the symmetry. In space-time geometry, the straight path through space-time between two events, the path where you don't accelerate, is always the path of maximum elapsed time. It's the longest path through the time dimension. Any path that deviates from a straight line, any path that involves acceleration and direction changes, covers less time. This is the space-time equivalent of the geometric fact that a straight line is the shortest distance between 2 points in ordinary space. But because of the minus sign in the space-time interval, in space-time it's reversed. The straight path is the longest in time. The curved or bent path is shorter. Anna's path through space-time is straight. Beth's path is bent. She goes out, turns around, comes back. Her path through space-time is kinked at the turnaround point. And kinked paths accumulate less time than straight paths. It's pure geometry. The same geometry that creates the speed limit, the same minus sign in the interval formula, also dictates that the twin who travels ages less. The twin paradox isn't really a paradox at all. It's a demonstration. It shows that the space-time budget isn't just an abstract concept. It produces real, permanent, irreversible consequences. The time you don't spend, because you spent your budget on spatial motion instead, is gone. You don't get it back. It's not waiting for you. It never passed for you in the first place. The years Anna lived while Beth was travelling are years that simply don't exist in Beth's experience. Beth didn't skip them or sleep through them. They never happened to her. Her space-time path was shorter through time, and that's a physical fact about the geometry of the path she took through the universe. This reframing changes everything. The speed of light isn't a barrier out there in the distance that you're trying to reach. It's not something you're approaching from below. You're already moving at that speed, right now, sitting in your chair. You're moving through space-time at the speed of light, all of it directed through time. When you walk across the room, you redirect a tiny, tiny fraction of it into spatial motion. The speed limit doesn't feel like a wall because it isn't one. It's more like a budget constraint. You can't spend more than you have, and you already have exactly the speed of light to work with. No more, no less. And this is why the speed limit is structural. It's not imposed by a force or a mechanism. It emerges from the geometry of space-time itself. The minus sign in the space-time interval formula, the one that makes space-time different from ordinary four-dimensional space, is what creates the budget. It's what makes space and time trade off against each other. It's what makes faster motion through space mean slower motion through time. And it's what establishes the speed of light as the universal conversion rate between spatial motion and temporal motion. Without that minus sign, without that geometric structure, there would be no speed limit. Speeds would add up as Newton thought. You could go as fast as you wanted, but you'd also lose causality. You'd lose the distinction between past and future. You'd lose the ability to say that one event caused another. You'd lose everything that makes the universe comprehensible. The speed limit is the price we pay for a universe with cause and effect. Or perhaps it's better to say that cause and effect are the gifts we receive because the universe has a speed limit. Without it, the causal architecture of reality would unravel in ways that are far more devastating than most people realize. We'll see exactly how later. But first, let me push in a different direction. Because understanding light cones changes how you see the universe in a fundamental way. Right now, sitting where you are, you have a light cone extending into the future. It encompasses every event in the universe that you could theoretically influence if you sent a signal at the speed of light. That light cone is expanding outward at 300,000 kilometers per second in every direction. Anything outside that cone is beyond your causal reach. You cannot touch it, signal it, or influence it in any way. And you also have a past light cone extending backward in time. It encompasses every event that could have influenced you, every event whose light or gravitational waves or any other signal has had time to reach your current position. Everything inside your past light cone is part of your causal history. Everything outside it is unknown to you, not because you lack instruments, but because the information hasn't had time to arrive yet. These light cones define your relationship with the universe. They tell you what you can know, what you can affect, what is accessible to you, and what is forever beyond your reach. The light cone structure doesn't just describe motion, it defines causality, information, knowledge, and influence. It is the architecture of reality. Every observer in the universe has their own set of light cones, and while different observers might disagree about the spatial and temporal coordinates of events, they all agree on the light cone structure. They all agree on which events are inside each other's light cones and which are outside. They all agree on which events can causally influence which other events. This is another invariant, like the space-time interval. The causal structure of the universe is observer-independent. It is absolute in a way that space and time individually are not. Einstein showed us that space is relative, time is relative, simultaneity is relative, but causality is absolute. The question of whether event A can influence event B has a definite answer that all observers agree on, and the answer is determined by whether B is inside A's future light cone. If yes, A can cause B. If no, it cannot. Period. No amount of clever engineering or advanced technology changes this. The light cone structure of spacetime dictates what is causally possible. This is the deepest reason the universe has a speed limit. The speed limit is not about speed at all. Not really. It's about the causal architecture of reality. It's about which events can talk to which other events. It's about the structure of cause and effect. The speed of light is the rate at which causal connections propagate through the four-dimensional geometry of spacetime. It is the speed of causality, and causality requires a maximum speed. Without one, every event could influence every other event with no delay, no separation, no ordering. The entire concept of before and after would dissolve. The speed limit is what gives the universe its temporal direction, its causal order, its narrative structure. It is what allows things to happen one after another in a way that makes sense. It is what allows the universe to have a history rather than just a jumble. Just how thoroughly a universe without a speed limit would unravel, down to the level of atoms and thermodynamics and the very possibility of structure, is something we haven't fully explored yet. And when we do, the answer turns out to be even more devastating than the causality argument alone suggests. And it arises entirely from the geometry of spacetime, from that minus sign in the interval formula, from the way space and time are fused together in Minkowski's four-dimensional structure. The speed of light is not a fact about light, it is a fact about reality. It is the exchange rate between meters and seconds. It tells you how much space equals how much time. 1 second of time is equivalent to 299,792 kilometers and 458 meters of space. That conversion factor is what physicists actually mean when they say the speed of light. It is the fundamental ratio built into the geometry of spacetime that determines how spatial distances relate to temporal durations. And it is why the universe has a speed limit. Because space and time are the same thing measured in different units, and the speed of light is the conversion factor between those units, it is why moving faster through space means moving slower through time. It is why your space-time budget is fixed. It is why cause and effect work. It is why the universe makes sense. This is the answer to the question we started with. Why does the universe have a speed limit at all? Because space-time has a specific geometric structure, a structure where space and time are unified, where the interval formula has a minus sign, where motion through space trades off against motion through time, where every object always moves through space-time at a fixed total rate. And that structure necessitates, absolutely and inescapably, a maximum speed for causal influence. The speed of light is that maximum, not because of anything special about light, but because of everything fundamental about space-time. And the consequences of this, the physical effects that emerge when objects approach this limit, have been measured, tested, and confirmed with a precision that would have been unimaginable a century ago. So far, we've established that the universe has a speed limit not because of anything special about light, but because of the geometric structure of space-time itself. Space and time are unified. Motion through space trades off against motion through time, and the total rate of motion through space-time is always fixed at the speed of light. This is an elegant idea, but physics isn't just about elegant ideas. It's about measurable, testable, confirmable reality. And the extraordinary thing about the speed limit is that it doesn't just sit there as an abstract geometric fact. It reaches into the physical world and produces consequences. Strange, counterintuitive, dramatic consequences that we have measured with breathtaking precision. These consequences aren't theoretical speculations waiting for confirmation. They are observed facts, confirmed thousands of times across decades of experiments, in laboratories, in particle accelerators, in orbit, and in the atmosphere above our heads. Let's walk through them one by one, because each one demonstrates that the speed limit isn't a theoretical curiosity. It is a structural feature of reality that shapes everything from the ticking of clocks to the mass of particles to the energy locked inside every atom of your body. The first and most famous consequence is time dilation. We've already discussed the concept. When you move through space, some of your space-time budget shifts from temporal motion to spatial motion. Your clock slows down relative to a stationary observer. The faster you move, the slower your clock ticks. At everyday speeds, the effect is unimaginably tiny, but it's real, and we've measured it directly. In 1971, two physicists named Joseph Hafele and Richard Keating conducted one of the most elegant experiments in the history of science. They took 4 highly precise cesium atomic clocks, put them on commercial airplanes, and flew them around the world. 2 flights went eastward, 2 went westward. When the clocks returned, they compared them to identical clocks that had stayed on the ground at the United States Naval Observatory. The results matched Einstein's predictions with remarkable accuracy. The clocks that flew eastward, travelling in the same direction as Earth's rotation and therefore moving faster relative to the centre of Earth, lost about 59 nanoseconds compared to the ground clocks. The clocks that flew westward, travelling against Earth's rotation and therefore moving slower relative to the centre of Earth, gained about 273 nanoseconds. These numbers included both the effects of velocity, the special relativistic time dilation, and the effects of altitude, the general relativistic time dilation caused by being farther from Earth's gravitational field. Both effects contributed, both were measurable, and both matched predictions precisely. 59 nanoseconds might not sound like much. It's billionths of a second, but the clocks were precise enough to detect it. And the result proved that time genuinely runs at different rates, depending on how fast you're moving and how deep you are in a gravitational field. This isn't a metaphor, it isn't an approximation, it is a measured physical fact. Clocks that travel at different speeds tick at different rates, not because they're broken, because time itself flows at different rates. A far more dramatic demonstration happens every second in particle accelerators around the world. The Large Hadron Collider at CERN near Geneva accelerates protons to within 1/1000% of the speed of light. At this speed, time dilation becomes extreme. A proton's internal clock runs roughly 7,000 times slower than a clock at rest. Processes that would normally take a certain amount of time in the proton's rest frame take 7,000 times longer from our perspective. We observe this directly. It's not inferred. It's measured. We can see unstable particles lasting far longer than they should because their internal clocks are running slow. The particles themselves don't know anything unusual is happening. In their own rest frame, they decay at the normal rate. But from our perspective in the laboratory, their lifetimes are stretched by factors of thousands because they're moving so close to the speed of light. Perhaps the most beautiful natural demonstration of time dilation involves muons. Muons are subatomic particles produced when cosmic rays, high-energy particles from deep space, slam into the upper atmosphere at altitudes of about 15 to 20 kilometers above the ground. Muons are unstable. They have a mean lifetime of about 2.2 microseconds. That means a typical muon survives for only about 2 millionths of a second before decaying into other particles. At this decay rate, even travelling at close to the speed of light, muons should only make it about 660 meters before most of them decay. They're created 20 kilometers up. They should be almost completely gone long before reaching the ground. But that's not what we observe. We detect enormous numbers of muons at ground level, far more than the simple calculation predicts. Why? Because the muons are travelling at about 99.94% of the speed of light. At this speed, time dilation stretches their lifetime by a factor of about 29. From our perspective on the ground, the muons live 29 times longer than they do in their own rest frame. Instead of 2.2 microseconds, they survive for about 64 microseconds in our frame. That's enough time to travel over 19 kilometers, easily reaching the ground from where they were created in the upper atmosphere. From the muon's perspective, the situation looks different but is perfectly consistent. The muon lives for its normal 2.2 microseconds, but from the muon's rest frame, the distance between the upper atmosphere and the ground is length contracted. The 20 kilometers between the point of creation and the ground shrinks to about 700 meters in the muon's frame. So the muon only has to travel 700 meters, which it can easily do in 2.2 microseconds at its speed. Both explanations, time dilation from our perspective and length contraction from the muon's perspective, give the same result. The muon reaches the ground. Two different observers describe the same outcome using different combinations of time and space effects. This is exactly what special relativity predicts, and we observe it happening continuously. Every second, muons created in the upper atmosphere survive their journey to the ground because time dilation and length contraction are real, physical effects. Not theoretical predictions, not approximations. Measured facts that you could verify yourself with a muon detector, which physics students around the world build as laboratory exercises. The most practically important confirmation of the speed limit comes from something billions of people use every day without thinking about it: the Global Positioning System. GPS satellites orbit Earth at an altitude of about 20,200 kilometers, moving at about 14,000 kilometers per hour relative to the ground. That's fast by human standards, but incredibly slow compared to light. Yet the time dilation effects at this speed are large enough to matter for precision navigation. Special relativity predicts that the satellite clocks, because they're moving relative to clocks on the ground, should tick about 7 microseconds per day slower than ground clocks. But there's also a general relativistic effect. The satellites are higher up in Earth's gravitational field, where spacetime is less curved. This causes the satellite clocks to tick about 45 microseconds per day faster than ground clocks. The two effects partially cancel, but the net result is that satellite clocks gain about 38 microseconds per day relative to ground clocks. 38 microseconds might sound trivial, but GPS works by measuring the time it takes signals to travel from satellites to your phone. Light travels about 300 meters in 1 microsecond. An error of 38 microseconds means a position error of about 11 kilometers. Within a single day, your GPS would be off by 11 kilometers. Within a week, it would be off by nearly 80 kilometers. GPS would be useless. Every GPS satellite has its clock rate adjusted before launch to compensate for relativistic time dilation. The clocks are deliberately set to tick at a slightly different rate so that once they're in orbit, experiencing the combined effects of velocity and gravitational time dilation, they tick at the same rate as clocks on the ground. This correction works perfectly. GPS positions are accurate to within a few meters. Every time you use GPS to navigate, to find a restaurant, to track a delivery, to hail a rideshare, you are relying on Einstein's theory of relativity being correct. The entire GPS system is a continuously running confirmation that time dilation is real and that the speed limit shapes how time flows throughout the universe. But the GPS example hints at something deeper that deserves its own discussion. It isn't just velocity that makes time run at different rates, gravity does it too. And this gravitational time dilation is just as real, just as measurable, and just as profound in what it tells us about the speed limit and the structure of space-time. Einstein's general theory of relativity, published in 1915, extended special relativity to include gravity. Einstein showed that gravity isn't a force pulling objects together the way Newton described. Gravity is the curvature of space-time caused by mass and energy. Massive objects like Earth, the Sun, and black holes warp the space-time around them. And this warping doesn't just bend the paths of objects moving through space, it bends the flow of time itself. The closer you are to a massive object, the more space-time is curved around you, and the more space-time is curved, the slower time passes for you relative to someone farther away. A clock on the ground floor of a building runs measurably slower than an identical clock on the top floor, not because something is wrong with the lower clock, but because time itself passes more slowly closer to Earth's centre of mass, where the gravitational field is stronger and space-time is more curved. This effect has been measured with extraordinary precision. In 2010, researchers at the National Institute of Standards and Technology used aluminium ion clocks so precise they could detect time dilation from a height difference of just 33 centimeters, about 1 foot. They placed one clock a third of a meter higher than the other and the higher clock ticked faster, by an amount so tiny it would take billions of years to add up to even a full second. But it was there, measurable, real. Time flows at different rates at different heights above the ground, not approximately, not theoretically, actually. Near a black hole, gravitational time dilation becomes extreme. A black hole is a region where so much mass is compressed into such a small space that space-time curves so severely that nothing, not even light, can escape. At the event horizon, the boundary of the black hole, time dilation becomes infinite from the perspective of a distant observer. If you watched someone fall toward a black hole, you would see their clocks slow down more and more as they approached the event horizon. Their movements would become sluggish, their heartbeat would slow, the light from their body would stretch to longer and longer wavelengths, shifting from visible light to infrared to radio waves. They would appear to freeze at the event horizon, their image becoming dimmer and redder, never quite crossing it from your point of view. Time for them, as seen by you, would effectively stop. From their own perspective, the experience would be completely different. They would cross the event horizon in finite time, feeling nothing unusual at the boundary itself. But they could never send a signal back to you, because nothing, no signal, no light, no information of any kind, can travel outward from inside the event horizon. The curvature of space-time is so severe that all paths through space-time, even paths travelling at the speed of light, point inward. There is no outward direction anymore. The speed limit still holds inside the black hole. Light still travels at 300,000 kilometers per second through local space-time, but the space-time itself is so warped that every direction leads deeper inside. The speed limit and the curvature of space-time conspire to create a region from which no information can escape. This is profoundly connected to the speed limit. Black holes exist because space-time can curve, and the maximum speed of causal influence means that once space-time curves enough, it can create regions that are permanently cut off from the rest of the universe. If there were no speed limit, light could travel infinitely fast and escape from any gravitational field, no matter how strong. Black holes couldn't exist. The very concept of an event horizon depends on there being a maximum speed that even gravity's curvature can trap. Length contraction is the spatial counterpart to time dilation. When an object moves at high speed relative to you, it becomes physically shorter in the direction of motion. Not squished by a force, not compressed by pressure, genuinely shorter because space itself is contracted for moving objects. At everyday speeds, this contraction is negligible. A car moving at 100 km per hour is shorter by an amount far too small to measure with any existing instrument. But at speeds close to light, the effect becomes dramatic. An object moving at 87% of the speed of light is half its rest length. At 99%, it's about 1/7 its rest length. At 99.99%, it's about 1/70th. And as an object approaches the speed of light, its length in the direction of motion approaches zero. This has been confirmed indirectly through numerous experiments. The muon observation is one example. From the muon's frame, the atmosphere is length contracted, which is why the muon reaches the ground despite its short lifetime. Particle collisions in accelerators also depend on length contraction. When two beams of protons moving in opposite directions collide at the Large Hadron Collider, the protons are flattened into pancake-like shapes by length contraction. Their collision dynamics depend on this contraction, and the results we observe match predictions that account for it. Now, let's talk about what happens to energy and mass as you approach the speed limit. This is where E equals mc squared comes in, and this equation, probably the most famous in all of science, is a direct consequence of the speed limit. Einstein didn't just pull this equation out of thin air, he derived it from the structure of space-time. The equation says that energy and mass are equivalent. They're the same thing, measured in different units. The speed of light squared is the conversion factor between them. Just as the speed of light is the conversion factor between space and time, c squared is the conversion factor between mass and energy. A small amount of mass corresponds to an enormous amount of energy because c squared is such a large number. About 9 × 10⁻16 in metric units. This means 1 kilogram of matter, if you could convert it entirely into energy, would release about 90 quadrillion joules. That's roughly the energy of a 20 megaton nuclear weapon. The energy is already there, locked inside the mass. E equals mc squared doesn't create energy, it tells you how much energy mass already contains. But E equals mc squared is actually the simplified version of a more complete equation. The full equation is E squared equals P times C, that quantity squared, plus m times c squared, that quantity squared. Here, P is momentum, m is rest mass, and c is the speed of light. When an object is at rest, its momentum is 0, and the equation reduces to the famous E equals mc squared. But when an object is moving, you need the full equation, and the full equation reveals something crucial about the speed limit. As you accelerate an object, you add energy to it. That energy increases its momentum, but it also effectively increases the object's resistance to further acceleration. In Newtonian physics, the relationship between force and acceleration is simple. Force equals mass times acceleration. Apply a constant force and you get a constant acceleration. Speed increases linearly over time without limit, but in special relativity, this breaks down at high speeds. As an object approaches the speed of light, it becomes harder and harder to accelerate it further, not because of friction, not because of any external force, but because the energy you're adding goes increasingly into increasing the object's resistance to acceleration, rather than increasing its speed. At speeds much less than light, almost all the energy you add goes into making the object move faster. At half the speed of light, a noticeable fraction starts going into increasing inertia. At 90% of the speed of light, most of the energy you add goes into increasing inertia. At 99%, almost all of it does. And at the speed of light itself, the energy required becomes infinite. You would need literally infinite energy to accelerate any object with mass to the speed of light. And since the universe doesn't contain infinite energy, no object with mass can ever reach it. This isn't an engineering problem. You can't solve it with better engines or more fuel or a more efficient propulsion system. It's not about the technology of acceleration, it's about the geometry of space-time. The same geometric structure that makes time dilation and length contraction inevitable also makes infinite acceleration energy inevitable. They're all consequences of the same underlying mathematics. The Lorentz transformations that describe how space and time change between reference frames also describe how energy and momentum transform. And those transformations, emerging from the structure of space-time, ensure that the speed of light can never be reached by anything with mass. Particle accelerators demonstrate this directly. The Large Hadron Collider consumes about 1.3 billion kilowatt-hours of electricity per year. It uses powerful superconducting magnets, cooled to temperatures colder than outer space. And with all this energy and technology, it accelerates protons to within 0.1% of the speed of light. Not 100%, agonizingly close, but never there. Getting each tiny fraction closer to light speed requires enormous additional energy for vanishingly small speed increases. The protons at the Large Hadron Collider have about 7,000 times more energy than their rest mass energy. All that additional energy, thousands of times more than the energy equivalent of the proton's own mass, gets them only marginally closer to the speed of light. Each tiny fraction of a percent closer requires dramatically more energy than the last, and 100% remains forever out of reach. This relationship between mass and energy has been confirmed not just in accelerators, but in the most dramatic way imaginable. Nuclear weapons and nuclear power plants operate by converting tiny fractions of mass into energy, exactly as E equals mc squared predicts. In nuclear fission, a heavy nucleus like uranium-235 splits into lighter fragments. The total mass of the fragments is slightly less than the mass of the original uranium nucleus. That missing mass, about 0.1% of the original mass, has been converted into energy. And that tiny fraction of mass produces enormous energy, because c squared is so large. The bombs dropped on Hiroshima and Nagasaki each converted less than a gram of matter into energy. Less than a gram. and the result was an explosion equivalent to thousands of tons of conventional explosives. In nuclear fusion, the process that powers every star in the universe, light nuclei combine to form heavier ones. Again, the products have slightly less mass than the ingredients. The missing mass becomes energy. The Sun converts about 4 million tons of matter into energy every single second. 4 million tons of mass vanishes every second, transformed into the light and heat that sustains all life on Earth. And it has been doing this for 4.5 billion years. This is E equals mc squared at work on a cosmic scale, and it only exists because the universe has a speed limit. The relationship between mass and energy is a direct consequence of the space-time structure that creates the speed limit. Without the speed limit, without the specific geometry of space-time, mass and energy would not be interchangeable. Nuclear power would be impossible. Stars wouldn't shine. The universe as we know it couldn't exist. Perhaps the most stunning confirmation that the speed limit belongs to space-time itself, and not merely to light, came on August 17, 2017. On that day, two neutron stars spiraling toward each other in a galaxy 130 million light-years away finally collided. The collision produced two completely different kinds of signals. It produced gravitational waves, ripples in the fabric of space-time itself, detected by the LIGO and Virgo observatories on Earth. And it produced a burst of gamma rays, the highest energy form of electromagnetic radiation, detected by the Fermi Gamma Ray Space Telescope and the International Gamma Ray Astrophysics Laboratory just 1.7 seconds later. Think about what this means. Two fundamentally different phenomena, gravity and light, travelling through space-time for 130 million years, across a distance so vast that the light left its source before dinosaurs went extinct on Earth. And they arrived within less than 2 seconds of each other. Gravitational waves are not electromagnetic radiation. They have nothing to do with photons, or electric fields, or magnetic fields. They are distortions of space-time itself, produced by the acceleration of massive objects. They are pure geometry, rippling through the fabric of reality, and they travel at exactly the same speed as light. Not approximately the same speed to within 1 part in 10 to the 15th, 1 part in a million billion. This single observation confirmed one of the deepest predictions of general relativity, and the deepest claim of this entire story. The speed limit is not a property of light, it is a property of space-time. Light travels at this speed because space-time dictates it. Gravitational waves travel at this speed because space-time dictates it. Any massless disturbance, no matter what its nature, will travel at this speed because the geometry of space-time permits no other value for massless propagation. The neutron-star merger didn't just detect gravitational waves and gamma rays, it proved that the speed limit is universal, fundamental, and structural. It belongs to the stage, not to any actor performing on it. There's another deeply important experiment that confirms the speed limit and everything that comes with it. In 2011, a research collaboration called OPERA announced results suggesting that neutrinos, ghostly subatomic particles that barely interact with matter, might travel slightly faster than light. The announcement sent shockwaves through the physics community. If true, it would overturn over a century of established physics. It would mean the speed limit was not absolute. It would call into question the entire framework of special relativity. Scientists around the world immediately began scrutinizing the result. Not because they were hostile to new discoveries, but because the claim contradicted an enormous body of confirmed evidence. Extraordinary claims require extraordinary evidence, and the evidence for the speed limit was overwhelming. Within months, the OPERA team found the source of the anomaly. A fibre optic cable connecting a GPS receiver to the experiment's timing system was not fully screwed in. This loose connection introduced a timing error of about 60 nanoseconds, which was exactly the size of the supposed faster-than-light signal. The neutrinos were travelling at very nearly the speed of light, just as expected for particles with an almost imperceptibly tiny mass. The anomaly was a loose cable. This episode illustrates something important. The speed limit has been tested so many times, in so many different ways, with such extraordinary precision, that when a single experiment seemed to show a violation, the physics community's first instinct was to look for an error. Not because they were closed-minded, but because the evidence supporting the speed limit was so vast and so strong that an experimental error was by far the most likely explanation. And they were right. The speed limit stood, as it always has. There's a beautiful symmetry in how all these effects connect. Time dilation, length contraction, the relativistic energy-momentum relation, E equals mc squared, gravitational time dilation, the identical speed of gravitational waves and light. They all emerge from the same source, the geometric structure of spacetime. They're not separate phenomena that happen to coexist. They're different facets of the same underlying reality. Change one, and you change all the others. They're locked together by the mathematics of the Lorentz transformations and Einstein's field equations. And those equations are simply the rules for how spacetime's geometry looks from different perspectives, and how it curves in the presence of mass and energy. If you change the speed of light, if you imagine a universe where the speed limit was different, everything else would change with it. The relationship between mass and energy would be different. Time dilation would scale differently. Length contraction would follow a different curve. Gravitational fields would behave differently. The entire structure of physics would shift. Every physical law that involves the speed of light, and there are many, would be altered. Electromagnetism would behave differently. Atomic structure would change. Chemistry would change. Biology would change. Stars would burn differently, or not at all. The universe would be fundamentally different in every conceivable way. Consider what would happen if the speed of light were much slower, say 100 kilometers per hour. Relativistic effects would be obvious in everyday life. Driving a car would produce noticeable time dilation. You'd age measurably slower during your commute. Objects moving at highway speeds would visibly shorten. The colours of approaching and receding objects would shift dramatically due to the Doppler effect. The world would look surreal, distorted by relativistic effects that in our universe only become apparent at speeds thousands of times faster. Now consider the opposite. What if the speed of light were much faster, say 1 trillion times faster than it actually is? Relativistic effects would be undetectable at any speed we could achieve. Time dilation would be unmeasurably small. Length contraction would be invisible. E equals mc squared would still hold, but c squared would be so enormous that even nuclear reactions would release incomprehensibly larger amounts of energy. Stars would burn differently. Atomic physics would change. The universe would look nothing like what we observe. The actual value of the speed of light, 299,792.458 kilometers per second, is what it is. We don't know why it has this specific value rather than some other value. It's a fundamental constant of nature, one of about 25 such constants that define the physics of our universe. These constants include things like the gravitational constant, Planck's constant, the mass of the electron, the strength of the electromagnetic force. Together, they determine every physical process in the universe. Change any one of them, even slightly, and the universe changes dramatically. Many physicists suspect these constants might be explained by some deeper theory, a theory that would show why the speed of light must have exactly the value it does. But we don't have that theory yet. For now, the speed of light is a measured quantity. We know it with extraordinary precision. We've confirmed its constancy in every experiment ever conducted. We've built our entire framework of modern physics around it, and every prediction that framework makes has been verified to remarkable accuracy. The precision with which we know the speed of light is actually so high that in 1983, the international scientific community redefined the meter based on it. The meter is no longer defined by a physical bar of metal in a vault in Paris. It's defined as the distance light travels in a vacuum in 1,299,792,458th of a second. The speed of light is now exactly 299,792.458 kilometers per second by definition. We've defined our unit of length in terms of the speed of light. That's how fundamental and how precisely known this constant is. We trust it more than any physical measuring rod. We trust it more than any artifact we could manufacture. We trust the speed of light so completely that we've built our entire system of measurement on top of it. Every experiment points in the same direction. Every measurement confirms the same truth. The universe has a maximum speed for the transmission of information and causal influence. This speed is built into the geometry of spacetime. It determines how time dilates, how lengths contract, how energy and mass relate to each other, how gravity curves the fabric of reality, and how cause and effect propagate through the cosmos. It is not a barrier that better technology might overcome. It is not a limitation of our current understanding. It is a structural feature of reality, as fundamental as the number of spatial dimensions or the existence of matter itself. The speed limit is not something the universe has. The speed limit is something the universe is. If the universe has a hard, absolute speed limit, a maximum rate at which information and causal influence can travel, then why do we keep hearing about things that seem to break it? This is one of the most common sources of confusion in all of physics, and it's worth addressing carefully, because the apparent violations aren't just interesting curiosities. Understanding why they don't actually violate the speed limit reveals something deep about what the speed limit really is and what it protects. Let's start with the most dramatic example, the expansion of the universe. Right now, as you sit here, galaxies far away from us are receding at speeds that exceed the speed of light. This isn't a theoretical possibility or a fringe claim. It's the standard, accepted, well-measured picture of modern cosmology. Galaxies billions of light years away are moving away from us faster than light. Some are receding at 2 or 3 times the speed of light. The most distant regions of the observable universe are receding at more than 3 times light speed. How can this be? Doesn't this violate everything we've established? No. And the reason it doesn't is one of the most important distinctions in all of physics. The speed limit applies to objects moving through space. It applies to signals travelling through the fabric of space-time. It applies to information, influence, and causal connections propagating from one event to another. But the expansion of the universe is not objects moving through space. It's space itself expanding. The galaxies aren't flying through space at faster than light speeds. They're sitting approximately still in their local regions of space. But the space between us and them is stretching. New space is being created between us and those distant galaxies. The galaxies are being carried apart by the expansion of the fabric they're embedded in. Think of it like raisins in bread dough that's rising. The raisins aren't moving through the dough, they're sitting still within the dough. But as the dough expands, the raisins get farther apart. 2 raisins that are close together separate slowly. 2 raisins that are far apart separate quickly because there's more dough between them expanding. If the dough is large enough and expanding fast enough, 2 raisins on opposite sides could be separating at a rate faster than any raisin could move through the dough. But neither raisin is violating any speed limit. Neither is moving through the dough at all. The dough itself is expanding. This is exactly what's happening with the universe. Space itself is expanding. Galaxies are embedded in space like raisins in dough. Nearby galaxies separate slowly because there's less space between them to expand. Distant galaxies separate faster because there's more space between them. And beyond a certain distance, the cumulative expansion of all the space between us and a distant galaxy adds up to a recession speed greater than light. This doesn't transmit information. You can't use the expansion of space to send a message faster than light. You can't use it to influence distant events. The expansion carries galaxies apart passively. No signal passes between them faster than light. No causal influence propagates superluminally. The speed limit is about motion through spacetime, about the propagation of causes and effects. The expansion of space is something different entirely. It's the growth of the stage on which physics plays out, not the motion of actors on that stage. This distinction matters enormously. It means there are regions of the universe we will never be able to see, contact, or influence. Light from those regions, travelling at the speed limit through expanding space, will never reach us, because the space between us grows faster than the light can cross it. There's a cosmic horizon beyond which we are permanently, irrevocably cut off. Not because of any practical limitation, because the geometry of expanding spacetime makes it structurally impossible. The second commonly cited apparent violation is quantum entanglement. This one confuses even people with scientific backgrounds because it genuinely seems like faster-than-light communication. Here's what happens. Two particles can be prepared in what's called an entangled state. In this state, certain properties of the particles are correlated. They're connected in a way that has no classical analogue. When you measure one particle's property, the other particle's corresponding property is instantly determined, no matter how far apart the particles are. Instantly. Not at the speed of light, instantly. If you entangle two particles and send one to a laboratory on the other side of the galaxy, then measure your particle here on Earth, the distant particle's state is immediately determined. The correlation is instantaneous. Einstein himself was deeply bothered by this. He called it spooky action at a distance and argued it meant quantum mechanics was incomplete. Surely, he reasoned, there must be some hidden information, some local variable that the particles carry with them that predetermines the measurement outcomes. The correlations would then be like a pair of gloves separated into two boxes. You open one box and find a left glove. You instantly know the other box contains a right glove. No spooky action required. But in 1964, physicist John Bell proved mathematically that no theory based on local hidden variables could reproduce all the predictions of quantum mechanics. The correlations predicted by quantum mechanics are stronger than any local hidden variable theory allows. And since then, numerous experiments have confirmed that quantum mechanics is correct. The correlations are real. They're stronger than any local theory can produce. The entanglement is genuine. So does this mean information travels instantly between entangled particles? No. And this is the critical point. When you measure your entangled particle, you get a random result. Sometimes spin up, sometimes spin down, with specific probabilities. You can't control which result you get. You can't choose to make your particle spin up or spin down. The outcome is genuinely random. Your distant partner, measuring their entangled particle, also gets a random result. But their random result is correlated with yours. If yours is spin up, theirs is spin down, or vice versa, depending on how the entanglement was set up. Here's the thing. Your partner, looking at their measurement results in isolation, sees nothing unusual, just a random sequence of ups and downs. They can't tell whether you've measured your particles or not. They can't extract any message from their results. The correlations only become visible when you compare your results with theirs, and that comparison requires classical communication, sending your measurement results to your partner through normal channels at or below the speed of light. You can't use entanglement to send a message faster than light because you can't control your measurement outcomes. You can't encode information in the random results. All you can do is generate correlated randomness, and correlated randomness, as strange as it is, doesn't transmit information. No one has ever devised a scheme to use entanglement for faster-than-light communication, and there are rigorous proofs in quantum mechanics, called no-communication theorems, showing that it's impossible in principle. Entanglement is real, the correlations are instantaneous, but no usable information crosses the gap. The speed limit holds. A third source of confusion involves phase velocity and group velocity of waves. In certain materials and under certain conditions, the phase velocity of a wave can exceed the speed of light. Phase velocity is the speed at which the crests of a wave move. In some media, wave crests can travel faster than light, but the crests don't carry information. They're just a mathematical pattern, a repeating structure in the wave. What carries information is the group velocity, or, more precisely, the signal velocity, the speed at which a change in the wave pattern propagates, and that speed never exceeds the speed of light in any known physical situation. Imagine a stadium wave. The wave pattern can circle the stadium faster than any individual person can run, but no person is moving around the stadium. Each person just stands up and sits down in sequence. The pattern moves fast, but the people, the physical entities, don't. Similarly, wave crests can move faster than light, but the actual physical disturbance, the signal, the information, never does. A similar illusion occurs with shadows and laser dots. If you shine a powerful laser at the moon and flick your wrist, the dot of light on the lunar surface can sweep across at faster than the speed of light. The moon is about 384,000 kilometers away. A small angular movement of your wrist translates to an enormous distance on the lunar surface. Flick your wrist fast enough, and the dot moves across the moon at millions of kilometers per second. But the dot isn't a physical object. It's not transmitting information from one side of the moon to the other. Each point on the moon's surface is being hit by a separate photon traveling from your laser at the speed of light. The dot is just the pattern of where those separate photons land. The pattern can move faster than light because it's not a physical thing, it's just geometry. No energy, no information, no causal influence passes from one part of the dot's path to another at superluminal speeds. Shadows can do the same thing. If a large object passes between a distant light source and a screen, the shadow on the screen can sweep across at faster than light. But again, the shadow isn't a physical object, it's the absence of light. And the absence of something can't carry information or transmit causal influence. These examples all share a common thread. The speed limit doesn't apply to patterns, appearances, or geometric projections. It applies to the transmission of information and causal influence. The dot on the moon, the shadow on the screen, the crest of a wave in a dispersive medium, none of these carry information from point A to point B at superluminal speed. They're illusions of motion, patterns that can sweep across distances without any physical thing actually making the journey. The speed limit is specifically about whether event A can cause event B. Whether a signal, a particle, an energy transfer, any form of influence can propagate from one location to another. And the answer remains absolute. No faster than 300,000 kilometers per second through space-time. Everything else is just pattern and geometry. Now let's consider perhaps the most profound question of all. What would a universe without a speed limit actually look like? We've established that the speed limit emerges from the geometric structure of space-time. But what if space-time had a different structure? What if there were no maximum speed? What kind of universe would result? The answer is deeply unsettling. A universe without a speed limit would be a universe without reliable cause and effect. We discussed light cones earlier, the geometric structures in space-time that separate events that can causally influence each other from events that cannot. Light cones exist because of the speed limit. They're defined by the maximum speed at which causal influence propagates. Remove the speed limit and the light cones open up completely. Every event can influence every other event. There's no separation between causally connected and causally disconnected. Everything is connected to everything, everywhere, all at once. In such a universe, the future could influence the past. With no speed limit, signals could travel backward in time, as we discussed earlier with the Lorentz transformations. Cause and effect would become circular. An event in your future could reach back and change your past. Your decisions could be altered by events that haven't happened yet. Paradoxes wouldn't be exotic thought experiments, they'd be the normal state of affairs. Could a stable, ordered universe exist under such conditions? Almost certainly not. The laws of physics as we know them depend on causality. The equations of motion, the conservation laws, the evolution of quantum states, all of them assume that effects follow causes, that the state of the universe at one time determines the state at a later time. Remove causality and these equations lose their meaning. You can't predict the future from the present if the future can reach back and change the present. You can't even define what prediction means. Thermodynamics would collapse. The second law of thermodynamics, which says entropy tends to increase over time, depends on having a well-defined direction of time. Entropy increases toward the future because causes precede effects, and certain processes are irreversible. Without a speed limit, without reliable causality, without a consistent arrow of time, the concept of entropy increasing becomes meaningless. Heat could flow from cold objects to hot objects. Broken eggs could unbreak. The past and future would be indistinguishable. Furthermore, without a speed limit, the concept of locality would vanish. Locality means that objects are influenced directly only by their immediate surroundings. A particle responds to the field at its location, not to the field at some distant point. Physics is local. Forces act through fields that propagate at finite speeds. Remove the speed limit, and you remove locality. Everything affects everything else instantaneously. Every particle in the universe would instantly feel the gravitational pull, the electromagnetic influence, the nuclear forces of every other particle, everywhere. The computational complexity of such a universe would be infinite. Nothing could be calculated or predicted, because everything depends on everything else simultaneously. Structure itself would be impossible. Atoms exist because electrons occupy specific energy levels determined by quantum mechanics. Those energy levels depend on the electromagnetic force propagating at a finite speed. Change the speed of light and you change atomic structure. Remove the speed limit entirely, and it's unclear whether stable atoms could exist at all. Without stable atoms, there's no chemistry. Without chemistry, there's no complexity. Without complexity, there are no stars, no planets, no life, no minds to contemplate the universe. The speed limit, far from being a restriction or a frustration, is what makes the universe possible. It's what allows cause to precede effect. It's what allows time to have a direction. It's what allows events to happen in sequence rather than all at once. It's what allows structure to form, complexity to emerge, and life to evolve. The universe doesn't have a speed limit, despite wanting to let things go faster. The universe has a speed limit because without one, it couldn't exist in any form we'd recognize. This brings us to the deepest insight of all. The speed of light is not really a speed. Or rather, it's not primarily a speed. It's a conversion factor. It's the number that tells you how much space corresponds to how much time. We established earlier that 1 second of time corresponds to nearly 300,000 kilometers of space. But here's the deeper point. That conversion factor isn't just a number. It's the exchange rate between the two currencies of spacetime. When physicists work in what they call natural units, they often set the speed of light equal to 1. Not 1 meter per second or 1 kilometer per hour, just 1, a pure number. In these units, space and time are measured in the same units. 1 meter of space equals 1 meter of time, which is the time it takes light to cross 1 meter, about 3.3 nanoseconds. In natural units, the speed limit is just 1. You can't go faster than 1. Because 1 is the conversion factor between space and time when they're measured in the same units. And you can't exceed the conversion factor because space and time are the same thing. Setting the speed of light to 1 isn't a mathematical trick, it's revealing a truth. Space and time are fundamentally the same. They're measured in different units for historical reasons, because humans experienced space and time very differently long before we understood they were connected. We measured space in meters and time in seconds because they felt different to us. But nature doesn't distinguish between them. Nature uses the speed of light to convert between them, just as nature uses other conversion factors to relate things that seem different but are fundamentally the same. Temperature and energy are fundamentally the same thing, related by Boltzmann's constant. Mass and energy are fundamentally the same thing, related by c squared. Space and time are fundamentally the same thing, related by c. The speed of light keeps appearing because it's telling us something about the deep structure of reality. It's telling us that the universe has a specific geometry, that space and time are woven together with a specific relationship, and that relationship determines everything else. The forces, the particles, the structure, the evolution, the very possibility of a universe with order and complexity and life. Every question about the speed limit ultimately reduces to one answer. The universe has a speed limit because spacetime has the geometry it does, and spacetime has the geometry it does because that geometry is what makes a coherent, causal, structured universe possible. Whether there's a deeper reason behind this geometry, whether there's something that explains why spacetime has this particular structure rather than some other, we don't know. It might be the only consistent structure possible. It might be one of many possible structures, and we happen to live in a universe with this one. It might be explained by a deeper theory we haven't discovered yet. But within the universe we inhabit, the speed limit is not a fact about light. It's not a limitation of technology. It's not a barrier waiting to be broken. It's the heartbeat of reality. The fundamental rhythm at which the universe connects cause to effect, relates space to time, and allows existence to unfold in an orderly way. Think about what we've covered tonight. We started with the simple observation that speeds don't add up the way Newton thought. Michelson and Morley showed that light's speed is constant regardless of the observer's motion. Einstein accepted this constancy as fundamental and worked out the consequences. Minkowski revealed that space and time are a single, unified geometry. We discovered that everything always moves through spacetime at the speed of light, with motion through space trading off against motion through time. We saw how this geometry creates light cones that divide the universe into causally connected and causally disconnected regions. We walked through the measured consequences: time dilation confirmed by atomic clocks on airplanes and muons in the atmosphere, length contraction confirmed by particle physics experiments, the energy-mass relationship confirmed by nuclear reactions, and the existence of every star in the sky. GPS satellites corrected for relativistic time dilation to function properly. We addressed the apparent violations: the expansion of the universe, which is space itself, stretching rather than objects moving through space; quantum entanglement, which creates correlations but doesn't transmit information; phase velocities and laser dots and shadows, which are patterns sweeping across distances without any physical thing making the journey. And we explored what a universe without a speed limit would look like. No causality, no arrow of time, no locality, no structure, no atoms, no stars, no life. Nothing recognizable as a functioning universe. The speed limit isn't a frustrating constraint preventing us from exploring the cosmos. It's the architectural principle that makes the cosmos possible. It's the reason time flows forward, the reason causes precede effects, the reason structures can form and persist, the reason you can sit here and think about these questions at all. Without it, reality would dissolve into an incomprehensible mess of simultaneous everything, where nothing happens because everything happens at once, where nothing is caused because everything causes everything, where the very concept of understanding would be meaningless because understanding requires a mind requires a brain requires atoms, and atoms require the precise physics that the speed limit makes possible. So the next time you hear that nothing can travel faster than light, remember that this isn't a statement about light. It's a statement about the universe, about its geometry, its structure, its deepest architecture. The speed of light is the speed at which reality propagates, the speed at which one moment connects to the next, the speed at which here becomes there and now becomes then. It is the most fundamental constant in physics, not because light is important, though it is, but because the relationship between space and time is the most fundamental relationship in all of nature, and the speed of light is that relationship expressed as a number. You are sitting still right now, but you are not motionless. You are racing through time at the speed of light. Every atom in your body is hurtling through the time dimension at 300,000 kilometers per second. You cannot feel this motion because it's your default state. It's what motion through space-time feels like when all of it is directed through time and none through space. But it's real. It's happening, right now. The speed limit isn't something out there in the distance, something that applies to rockets and particles but not to you. It's something you're experiencing this very second. You are moving through space-time at the speed of light. You always have been. You always will be. The only choice you have is how to divide that motion between space and time. And that choice, that simple geometric trade-off, is what gives rise to every strange and beautiful consequence of relativity. Time dilation, length contraction, mass-energy equivalence, causality, the arrow of time, the structure of the universe. All of it flows from one fact. Space-time has a geometry, and that geometry has a speed. Thank you for taking this journey through the deepest structure of reality. If you found it valuable, a like or subscribe helps me keep making these explorations. And remember, the universe has a speed limit not because it can't go faster, but because faster doesn't exist. The speed of light is not a wall. It's the edge of the map. Beyond it, the map doesn't continue. There is no beyond. There is only space-time, structured and beautiful and absolute, connecting every cause to every effect at exactly the right speed to make existence possible. Good night.